Greetings. My name is John Gabriel, and this is the New Calculus channel. And if you'll recall, in a previous video, in this video here, I talked to you about some mainstream misconceptions, and I mentioned how mainstreams don't actually see these propositions correctly and don't understand that there are no axioms or postulates in mathematics. And in this particular video, I'm going to focus on one of the propositions that I talked about in this video here, mainstream misconceptions of geometry and mathematics. Okay, so let me begin. This is the proposition here. And what it says is basically this, that the length of this line here, AE, times EC, the length of AE times EC is equal to the length of DE times EB. Okay, I've actually written this incorrectly here. It's actually AE over EB and DE over it's AE over EB and DE over EC. Okay, so actually I could correct that very quickly. If you just bear with me, it's AE over BE oh dear. Anytime I'm in a hurry, I run into plot. No, I'm sorry, I did the wrong one there. AE over BE, and that will be DE over EC. Is that correct? Let's see now. So it's AE over BE and DE over EC. Yes, which basically means that AE times EC is equal to DE times BE, okay? And you would think that it doesn't matter how these lines are positioned, okay? They can be positioned any way you like. See that? And that product will always be the same, right? So at this stage, we haven't actually identified anything like similar triangles. The proposition in Euclid comes much later, only in a later book. So all this here has been done using rectangles. In other words, a measure of area, contrary to what Wilberger said in the last video, that there was no measure by Euclid. There was always measure. And this theorem is pretty hard if we don't know, if we're not aware of a previous proposition. But one thing that should come to mind here is, why should this property be true? For example, I mean, if the figure here were not a circle, would this identity here still hold? In other words, if we had a square and we just had these two lines crossing each other anyway, would this identity here hold? And you'd find out pretty soon that it wouldn't hold, okay? Because the triangles that are so formed wouldn't necessarily be similar. Okay, so, and this is interesting because right now we cannot use the theory of similar triangles. We have to use what we have. So we go back to this proposition here, and I'll tell you that, I'll explain this here very quickly to you, but I'll tell you first that it's not correctly interpreted in Sir Thomas Heath's Elements, okay, translation of the elements. So for example, he's got something down here. Where is it now? It's 35. Oh, we need to go to book 2 and proposition 5. Book 2 and proposition 5. And we'll see now that, first of all, this gnomon here is misinterpreted. And obviously the formula that's given down here is not what it's referring to. And what I've done is I've copied this formula into, so this here is the formula according to Heath, and this is obviously not even relevant. It's not even appropriate. It's got nothing to do with the proposition. It's just a different form, but it doesn't assume the facts of the proposition, which says the rectangle contained by the unequal pieces of the straight line. This here, blue and red, is the rectangle contained by the unequal pieces, okay? The blue and red areas. Plus the square on the difference, which is this green square, is equal to this black square here. That's what it's saying. None of this rubbish here, which is basically just a consequence of the simple proposition. And I've shown you here that it's true. If you take this area plus this area plus this area, you'll have 16. It's not true that if you take 4 plus 12 plus 3 that you'll have 16. Nope, because this gnomon here gives you 16 plus 3 is 19, which is not equal to 16, okay? So what this says here in the ancient Greek is precisely what I've explained to you. It's this gnomon here, okay, not this one, as you see in the book. So what it has that, but that's incorrect. It should be this one here, all right? So this dotted line shouldn't be over here, it should be over here, and it should be this gnomon. Okay, but at any rate, this is a very beautiful proposition which leads up to the one I just showed you, this one here, which would be almost impossible to prove without it. And you'll see that it doesn't matter how any two straight lines cut in a circle, the product of the blue and the red in each case will always be the same, okay? And later on, when we learn the theory of similar triangles, this is very easy to prove. Now, in ancient Greece, when they were talking about magnitudes, they knew the measure of the line AE. It was this particular magnitude here. So they would write AE rather than the actual number, which was given to name this particular distance, okay? And in most cases, some of these distances cannot be described by a number, only approximated, right? And so what happens is that you end up with two similar triangles. You see these green, red, and blue similar triangles? And we know they're similar because all the angles are equal. Vertically opposite here, these are subtended on this arc, and these angles here are subtended on arc AD. And so it shows you that the Greeks didn't even need to have the measure in terms of numbers. All they did was prove in terms of the area, which was described as a rectangular area, how this proposition is true. In other words, you can take any two straight lines in a circle, and the product of the lines where they meet at a particular point E, as you see here, so AE times EC would always be equal to DE times EB. Okay, and later on, as I said, it's very easy to prove using similar triangles. And so the ancient Greek here is not easy to understand. I can appreciate how Sir Thomas Heath and other translators could have gotten it wrong. But what really stuns me is that people like Wildberger and many others actually miss these things but claim to have studied the elements. The fact is that mainstream academics have never understood the elements. I was the first after Euclid, and before myself, obviously, before any mainstream academic, to understand these things, to understand the concept of number, the fact that there are no axioms or postulates in mathematics, and they're not required, and in fact an axiom is the same as a belief. So, at any rate, I hope you've enjoyed this little presentation. I would encourage you to download this book here because it's got the ancient Greek plus the English as well, and you can compare them side by side. Of course, I can read ancient Greek, so it's a lot easier for me to see if something has been translated correctly or incorrectly. And at any rate, that's just something I wanted to point out, because I'm going to be following up on my next video in What Your Ignorant Teachers Could Not Tell You. And I wanted to fit these 2 videos in before I continued on part 5. So this is a new calculus channel. My name is John Gabriel. Till next time, goodbye.